Assalamu alaikum, everyone. Today, our lecture is on LED. This is the continuation of our previous lecture, which is laser. Okay? So that is actually chapter 3 in our reference book of Agrawal. There, we actually discussed on various laser principle. Actually, the PN junction, like homo junction and hetero junction, and choice of material for semiconductor devices, right? Okay, as a continuation, we will actually study LED, light emitting diode, and laser. Okay, so what the principles of the LEDs are? It's actually forwarding biasing of PN homo junction. So LED uses a forward bias of a PN homo junction. Here, this is a typical PN junction is given, and it is actually forward biases. So if we want to bias a forward this PN junction, then this is P, means this has to be positive so that it can supply is the majority carrier, which is hole, and negative is connected. So in N-type material, what is there? Majority carriers are actually electron, right? Electrons. So this is also negative. So carriers will be supplied. And in P-type, majority carriers are electron. Actually, majority carriers are actually holes. So majority carriers are actually holes. So the positive holes will be supplied from this positive terminal. Thus, this is forward biased. So if we go back to our laser principle, we have seen there are three mechanisms involved, right? One is absorption of electron from valence band to conduction band, right? Absorption from valence band to or higher energy band. Then spontaneous emission means when it's fall back, this higher energy electron radiates in form of a light and other source of energy. And stimulated emission means actually this follows and others electron follows it. So this is absorption. This is spontaneous. This is stimulation, stimulated emission. In our laser, we have seen that laser use this is stimulated mechanism. For LED, it uses spontaneous emission. So it actually uses spontaneous emission. We have seen in our noise mechanism previously, where we discussed about various noise sources, namely thermal noise, which is common to all the electronic devices or optoelectronic devices, thermal, shoot, and read noise, right? When we say noise limited system, we have actually discussed this explicitly about shoot noise. Shoot noise actually is due to this spontaneous emission in a laser or in a light emitting device, which is actually in our case LED. Okay, so radiative recombination of electron hole pair in the depletion region generates light. So how the light is generated? Light is generated due to the radiative recombination. So from here, we know there are two kind of recombination, right? One is radiative or another would be non-radiative. We'll discuss more. So the emitted light is incoherent with relatively wide spectral range. From this schematic diagram, we have seen from the P and N-type material, with their conduction, with their this contacting point, lights emits, right? Okay, and these lights, when it emits, this has a very wide surface area, very wide surface area. And when lights emits, for example, a photon emits, it can go this direction. If it goes this direction, where the angle is actually theta c, critical angle, then if it's more than the critical angle, then total internal reflection happens. Means actually this is totally becomes lossy. And due to this wide surface area, the spectral width also is very wide. If I draw a spectral width of a LED, it would look like this. If this is actually power, if this is power or energy, power, then if this is actually wavelength, lambda, then the spectral width is actually very wide of a LED. Because of this very wide surface area. And photon can generate at any point, here, 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 means there will be no connection between each other. Like this photon generates independently. That's why they are incoherent. They are called, when we call incoherent, means for example, one photon generates, it goes this direction, another photon generates, it goes this direction, another photon goes this direction. You see, because of this change of they are not coherent, they are not similar. For example, when something is coherent, then there will be two phenomena in coherency. For example, something is coherent. Coherent means their direction and phase will be same. The direction of the generated light or photon, its direction and the phase will be similar, like these two. They are coherent. But if the direction is not similar, also the generation, their phase also is not similar. That's why incoherent. That's actually the reason the spectral width actually is very wide. That's the reason it becomes very wide, unlike the laser. Okay. So, okay. So, regarding the characteristics of a LED, like when we discuss about the characteristics of an LED, we should know something, which is excess carrier. What is excess carrier? Excess carrier is nothing but the minority carrier. Okay. So, what is a minority carrier? You probably know from our electronics courses or in PN junction. For example, if we have a pure silicon intrinsic material, we call it intrinsic material. When we dope it or make it impure by combination of another material, silicon is in the outer shell. There are 4 electrons. If we add 3 or 5 outer electrons molecule like gallium arsenide, blah blah blah, then it creates P or N. Okay. Okay. In P material, the majority carriers, in N, the major carriers are electron, right? The majority carriers are electron. The majority carriers are electron. What is the minority carrier in N? The minority carrier in N is holes. Oppositely, in P, the majority carriers are actually hole. The majority carriers are holes. What is the minority carrier? In P, electron. The minority carrier, the numbers are very low, quite insignificant, like 1 to 2% maximum. So they are called the minority carriers, or in other way, they are also called excess carrier. Now, the excess carrier is created by carrier injection, because we are make it as a forward bias, so we can inject the carrier. Okay. Excess carrier recombines either radiatively or non-radiatively. What does it mean? We actually already found this word, radiative recombination. So we know there are two kinds of recombination. One is radiative, another is non-radiative recombination. Okay, when we call it radiative or for example radiative recombination, for example, if an electron from here, when it falls from its conduction band to the valence band, non-radiatively, okay, let's discuss radiatively. When an electron from its higher energy band, means conduction band, falls to the valence band, means lower energy band, if it's radiate the excess energy, like how this process happen, the electron always choose or prefer to be in the valence band, but because this is a lower energy band, electron always wants to stay in the lower energy band. Because of this, it may make it stable. So if you give him excess energy, then it can go to the conduction band. Eventually, that is we call absorption in our system, right? Absorption. Eventually, if it falls down, what will happen? If this electron falls down to the conduction band to the valence band again, that excess energy which was required, like E, h nu, that amount of energy that must be released. If it's released in the form of light, or we call it photon, then this is called radiative. This nature is called radiative nature. If this electron in the higher energy band, if it falls to the lower energy band or conduction band to valence band, and the excess energy, which is h nu, which was absorbed when it goes from here to here, it had to absorb this same amount. When it has to release, if it comes back from conduction band to the valence band, it has to release this extra energy. If that extra energy is released in a form of heat or vibration, then we call it non-radiative. That is the difference between the radiative and non-radiative. Means this recombination can be in terms of radiative recombination or non-radiative recombination. Okay. Okay. So we know some of the definition, right? Okay. Let's see. So in equilibrium condition, what happened? Okay, in equilibrium condition, constant current flow into an LED. That happens actually in practical. In equilibrium condition, constant current always flows in an LED. So what does it mean actually? Means actually the injected current, it means that injected carrier, not current, the injected carrier, which actually we are injecting by making it as a forward biasing. Okay. So the injected carriers will be equivalent to the excess densities of the electrons and holes. Means the injected carriers are the equal to the excess densities of the electrons and holes, which is actually in room temperature, for example. What happened when we supply this energy, like when there is a constant current flow, what happens? For example, there is no connection. What happens? They goes to a like steady state kind of situation, right? Now, what we are doing, we are actually giving him an injection by this. By this, we are giving the injection. Okay. So the injected carriers in here, the carriers means both the electron and holes. The carrier means the holes, electron and holes, are the excess density of the electron and holes. Means actually this reason, this injection is the reason for the excess amount of supplied. For example, because of this is negative, so we have lots of negative charge, supply of negative charge. Because this is positive, so you will have lots of positive charge, supply of positive charge. So in constant current flow, then injected carriers means the holes and electron and holes, they will be same as the densities, excess density of the electron, because this is who is the reason for this excess densities. There is an electron and holes, of course there is carriers means electron and holes. Who actually is reason for this excess densities of electron and holes? This is injected current. How much these injected carriers are supplying, that causes excess electrons and holes in the system. Here excess electrons, excess holes, excess holes in this system, right? Okay. Or so the same thing can be said in other words, that external supply rate, which is actually injection rate, actually the external supply rate is radiative rate and non-radiative rate both together. Okay, when we have external supply, what happens in this mechanism? When we have external supply, what we have, the electron hole pair combined, isn't it? Electron, for example, if I give it this p and n junction, for example, these two, and if for example we connect them together, p and n, and we forward bias together, p equal to positive, n will be connected to the negative, what will happen? There are lots of negative charge supplying here, lots of positive charge supplying here. So this positive, excess positive will goes to the negative, so electron hole recombination is happening. So this external supply is causing the recombination, which is actually combination of the radiative and non-radiative both. Means portion of this will be emitted by this mechanism when this recombination happens. For example, in P and N, when we connect it as a forward biasing and we supply enough negative, 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 and positive, 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 what will happen? Every in their because they are sandwiched together now. If we close them, bring together, then it will be like this. So what will happen? So this electron and hole, they will recombine each other. This recombination will be both way. Either when it recombines, means higher energy of electron falls down to the lower energy. It may release as a photon, or it may release as a heat, which we call it phonon, non-radiative. So when this recombination happens, it can happen as a photon or a phonon, which is we call it radiative and non-radiative. So the rate, external supply rate, will be equivalent to the rate of the radiative rate and non-radiative. For example, just give an example. If there are like 100 of extra electron or excess carrier you are supplying, then for example, if 50 is doing radiative and then other 50 is doing non-radiative, like that. Okay, so what is the external supply? External supply is nothing but this equation. J by QD, where J is the current density and Q is the charge, electron charge, and D is the thickness of the recombination region. Where in our cases, this is the thickness of this recombination region, right? This is like how much is the thickness of this recombination region. For example, it is happening within this region. For example, this is D, thickness of this recombination region. Okay, so which will be equivalent to the radiative rate. Radiative rate is this, and non-radiative rate is this. Where N is the excess electron density, which is actually this one, injected, because of this injected carrier causes the excess electron density, and tau is the carrier lifetime. So carrier lifetime is explicitly depends with the non-radiative recombination. Okay, this whole equation is called the rate equation. This is actually the fundamental equation by which we actually quantify LED or laser. Laser also has a rate equation. For LED, this rate equation is quite simpler. Okay. Now in equilibrium, this has to be 0. It means there has to be equal. Means this excess electron density has this relation. Means actually this relation gives the steady state electron density, because they comes to the steady state because they are now in equilibrium density in the active region when a constant current is flowing through this PN junction. Okay. So okay. So we know from the rate equation, we have the relation of this excess electron density in. Now we like to know what is the internal quantum efficiency in INT, for example, denoted by what is internal quantum efficiency. Actually, there are means from the name itself, there could be external quantum efficiency. Now we are actually inside of this mechanism of LED. Where you see we are in the inside. We are looking inside of this LED, right? So we are trying to know what is the efficiency. Actually, it is actually efficiency. We name it quantum efficiency because it happens in the quantum level. Okay. So what is that internal quantum efficiency? Is nothing but is the fraction of the electron hole pair that recombines radiatively. Means how much of it becomes. You see here there are two mechanisms happens, right? We have seen it. We have seen it that radiative rate and non-radiative rate. Non-radiative rate is not any effective stuff because it ultimately converts to the heat or vibration. Means it do not create any photon or light, which is actually general purpose of our LED, right? To create a light or photon. Means actually we have to find how much, what is the efficiency that radiative recombination is happening. That's actually our goal. Okay. So what is the radiative recombination rate? What is the radiative recombination rate? In comparable to the total recombination rate is called the efficiency. That makes sense, right? It is a like radiative is partial and total is the total. So partial to total something is always gives us the efficiency or something. Okay. So radiative recombination rate is this, and non-radiative is this. So radiative plus non-radiative makes it total, right? Total recombination rate. This one. Okay. So for exponential decay of the excess carrier, if the excess carrier makes exponential decay, if the carrier makes exponential decay, then the radiative recombination lifetime tau r is expressed by this equation, and tau nr non-radiative is expressed by this equation. So now we actually put it back. So if tau r equal to n by r, what will be the r? R is nothing but n by tau r, right? Same thing is for this one. R of nr is nothing but n by tau nr, right? These two value we will be put back here. So okay, so we want to find the internal quantum efficiency. Okay, solve it. We will actually end up with this relation. So now, or we actually can express the internal efficiency is expressed by this equation, where tau is the radiative decay. You see where this tau comes from this tau. This is actually the carrier lifetime total, right? And this tau nr is the non-radiative. This is the lifetime for the non-radiative carrier. So this tau is the total carrier lifetime, and this is the carrier lifetime for the non-radiative. Okay. Now from direct band gap semiconductor, for example, for a what are the direct band gap semiconductor? We have learned it earlier. Direct band gap. What are the direct band gap semiconductor? Gallium, gallium aluminum arsenide, right? Gallium aluminum arsenide, or indium gallium arsenide phosphide. For this kind of direct band gap material, these are of radiative and rate of radiative and rate of non-radiative in R. This one, the radiative recombination rate and non-radiative recombination rate. These two, they are almost 50%. They are almost 50%. Means for if you want to create a LED by using them, then it's only 50% efficient. Because if non-reactive takes 50%, means it's actually convert to heat, so it's not a very good use. So what do you have to do to increase this quantum efficiency? Because so far we created this LED by homojunction. You see, LED actually is a homojunction. Means actually you have to create LEDs by heterojunction. Then you can increase its efficiency. Okay. So that's all about our LED. Let us see if we can use an example here. Okay, this example is actually example 4.5 of our reference books of Kaiser. Is given a double, so let's say a double heterojunction indium gallium arsenic phosphide LED emitting at a peak wavelength at 1310 nanometer probably has radiative and non-radiative recombination time of 30 nanosecond and 100 nanosecond respectively. Okay. So also is given the drive current. The drive current is given. The current is given, or the current is 40 milliampere. Now, what is our tau? Let's find this tau. What is this? What is that tau? Let's see. This tau. What is this tau? This is called bulk recombination lifetime also. So we didn't know where. So this is called, this tau is called bulk recombination lifetime. So what is tau then? Tau is okay. If we rewrite it, 1 by tau is given there. So tau will be nothing but the tau r to tau in r by tau r plus tau in r, right? We know tau r, tau n r is one is 30 nanosecond and is 100 nanosecond. So 30 into 100 and 30 plus 100. All are nanoseconds, so we're not writing. So which is actually 23.1 nanosecond. That is actually the recombination lifetime. Okay. So what is the efficiency? Quantum efficiency in internal efficiency is nothing but we find it earlier, tau by tau nr, right? So tau by tau nr. So this tau is, we just find 31 1 nanosecond. Our tau nr is 30 nr. This is not nr. This is r. This is r. This is r. R recombination. So the recombination is 30 nanosecond. So 30, which is actually 0.77. So you see, this is 0.77 efficient. So 77% efficient actually, if you convert it in percentage. Okay. Okay. So what will be the this is internal efficiency? So everything will be internal. So what will be the internal power? Internal power, for example, of this laser int, for example. Internal power is nothing but the always connection to the efficiency, internal efficiency into the rate of current, rate of rate of photon generation, which will be I by Q. Okay, rate of photon generation. So this is actually rate of photon generation combined with its efficiency. That will be the practical rate of photon generation into h nu, the energy h nu. Now you can actually find that in int you can keep it I by Q. You can keep it I by Q h nu, right? H is h, and nu is nothing but c by lambda, because we here the wavelength is given. That's why we bring lambda here. Okay, just put everything. int is 77%, right? 0.77. I, what is the current? Drive current is 40 milliampere, right? Yeah. The current, okay, current is given. Q is the charge of the electron. H Planck's constant. C is the velocity of light, and lambda is the wavelength. So put all those values, you will get some 29.2 milliwatt. That is actually our answer. You see, so we could actually connect with our theory that okay, this is actually the power, the internal power. Means actually this power is before any loss. Okay, there might be any loss, so loss will be deducted from there. So internally, this amount of power will be generated from an LED of this combination. Then actually you count your how much power you need, how much loss in the coupler, how much loss in the connection, blah blah blah. That based on this, you actually find what is the internal power of your system. Okay. Okay, that's all about our LED lecture. Assalamu alaikum.